thinking for such a lovely introduction. I'll try and move up to it. So, I'm going to talk about soft astronomy, so puns intended, not hardcore. Yeah, so I've had some pictures here of some things that you might think of as soft. So in this one is a mass spring model. So it's an n-body simulation with springs. And it's not a round body, and it's under a tidal field. It's in an eccentric orbit around a planet or something, and so it tumbles. So this is a situation with non-principal axis rotation, and the object in the solar system that's most well known for undergoing this type of motion is Hyperion, actually. So this is a set of images from the OREX mission, which was went to Bennu. It's actually planned to have a sample return that will come back next year. So this is a near Earth orbit crossing asteroid, and just rubble, right? So, and it's got this funny top shape, which probably means it's deformed. And that is Mars, and it has this big crack in it, this canyon, which I'm calling a crack, but that's Valles Marineris. So I'm going to talk about, ways you can think about objects in astronomy that are solid. They may be elastic, they can deform. And in particular, I got really heavily involved in the spin dynamics part of it. So, oh, I'm supposed to take off my mask. Okay, yeah, okay. Yeah, just let me know. So, so the picture of Mars, I was kind of curious about, so the explanation for Valles Marineris involves stress relief from a buildup of volcanic province associated with Olympus Mons. But when you look at things on Earth, right? So this thing over here, this is the Great African Rift Valley, is a tectonic setting. Tectonic means slow divergence of continental plates, but there's a big rift building. And we think of that as happening on geological timescales. And this thing is a Barringer crater, which is an astronomical event that happened in maybe minutes. But originally, the proposal that was a crater from an impact was very controversial, and that's because it's on Earth, right? So we're people used to thinking about things happening on geological timescales. And so you could maybe try to turn this around and say, when we see that in space, we automatically assume that it's something that happened instantaneously with an impact. But when we look at something like this, we immediately all still think of it as a geological process. So an example, so while I was working on this, New Horizons mission came back with this lovely image of Charon. It has craters on it, and then it has these big rift valley. And the most explanations for it are geological, meaning it took lots of time. But why does it have to be? Maybe it happened quickly. And so one possibility would be, so impacts, strong impacts that actually are catastrophic happened in the early solar system. So if one of the examples of the Earth-Moon formation, where this happened because a really big thing hit the proto-Earth, which was called Theia. But if there were big, strong impacts in the early solar system, there were also big near misses. And the near miss means there's a strong tidal force. And tidal forces are different than impacts because they are tensile, they pull instead of compress. And when you pull something, you can make a crack. So that's the basic thing where basic idea. So how strong an encounter do you need to cause a crack in a moon? So if you have tidal deformation caused by a tidal encounter, you could think about what the velocity, what the tidal force is, and so that, yeah, I never wind up having my mouse work on this. Any case, the force depends on the radius of the object and the pericenter distance, which I've written here as Q. And using the impulse approximation, you can guess at the size of the velocity perturbation on the surface caused by that. And so that's just the tidal force times an encounter time scale. And then supposing the object is elastic, then you can equate the kinetic energy to the elastic energy. And so that the elastic energy depends on how much you've deformed the body. And so I've written that down in terms of this epsilon thing, which is the strain. That's the change in length divided by the length. So it's a unitless quantity describing how much you've deformed the body. So that tells you what the strain would be on the object caused by a strong tidal encounter. It depends on the mass ratio. But the key parameter that tells you whether it's important or not is the gravitational binding energy divided by the mass of the primary body. And then, so this is something you can estimate to order of magnitude, but the biggest problem then is now trying to understand when is this strain important? Like when is it big enough that it would actually cause to exceed the yield stress, and then you get tensile failure. And then the other big uncertainty is what are the elastic modulus? That's the elasticity of things in space. So we don't necessarily know what the elastic modulus of ice is in a moon, for example. So what strain would something like ice fail at? And so you can go look up rough values based on glaciers, for example. And it turns out to be less than 1%. And estimating binding energy is pretty straightforward. Elastic modulus, again, there's uncertainty. But so if we take the elastic modulus of ice, which is maybe somewhere around 1 to 10 megapascal region, what that tells you is that in order to have brittle failure, so that's when you exceed the yield stress, you need to be in a strong tidal encounter regime, which means you need to have a body that's nearly the same size undergoing a really close encounter. So one thing I noticed in this is when you take the strain rate and you divide by the gravitational timescale or the timescale for the encounter, you get what's called the strain rate, which is about 10 to the minus 6 per second. So geological things happen on much orders of magnitude lower strain rates, so like continents moving. But laboratory experiments are not necessarily that far off for high strain rates. So this is part of the challenge for trying to say something about what would happen to a moon under a strong tidal encounter is if you're thinking in terms of geological processes, it's really hard to figure out when they apply and when they don't apply because the tidal encounter regime is really different. So so let me show this in a different way. Now I need another hand. So I think this is probably charged. Oh, is this charged now? But I can't do demos. Oh, okay, great, wonderful. Okay, I'll just put that in my pocket. Okay, is that better? Yeah, so this is silly putty, right? So you're used to thinking about the center of the Earth as, being ductile because we have, motions inside the center of the Earth, but seismic waves go just through the Earth just fine. So it's elastic. And so this is, elastic. This out of order. But if you take your silly putty and you pull it enough, it breaks. Okay, so so this problem is in the elastic brittle setting, and that means masses and springs. So the springs give you the elastic phenomena, but then you have to decide how do I make a simulation give me brittle phenomena, which means, so in this particular case, I measured the strain, which is how much the springs are pulled, and then I mark things if it goes above some level. But in any case, this shows you one of our early simulations of a tidal encounter. It's a really soft body that's just barely holding itself up against self-gravity. You can see it oscillate. So those are normal modes, essentially. I used the graphics engine on Rebound because it had this really nice OpenGL viewing. It really helps to be able to see what's going on in this setting. And then Rebound had this really nice way of adding additional forces. So I just added springs. So springs are just, you take some length and you apply a force between the point mass particles. So these look like they're spheres, but they're really point mass particles. So the nice thing about, so this is a random mass spring model. There was some ideas in the graphics simulation community by this guy, Matthew Cott, who actually works in Japan now. I think he's Polish, but he showed that this random mass spring model where you generate the particles randomly and then hook up springs between particles of, that are within some particular distance, that it had a nice continuum limit. So you could take the number of springs per volume and use the spring constant to get the Young's modulus. And the so despite the fact you're like inspired by graphics community software, they're trying to make blobby things. We need to actually be able to compute real physical quantities from the simulation. So that made a real difference in this ability to simulate a solid. So yeah, so that's a tidal encounter. So this is what it is. It's nothing complicated. It's just you add elastic forces that depend on the length of the spring compared to some rest wavelength. And then we also added damping. I added damping initially because I wanted a stable system. And here's the strain rate. It's just this, how fast the length of the spring changes compared to the rest. So when you rest length. So when you have a damped spring model, that's a viscoelastic spring setting. So because you're turning energy into heat through the damping parameters. But one thing to notice is here is the forces, both of the forces, the damping forces and the elastic forces, are all applied between point particles equal and oppositely. And so that means it's going to conserve momentum and it's going to conserve angular momentum. So that's great. It's like, so it sounds really simple. It is really simple. So this is a low complexity code that can accurately model dynamics of viscoelastic materials and conserves angular momentum. So yeah, so that means it's really powerful. And we can do a lot of stuff with it. So when I was figuring this out, I was like, wait a minute, this is too easy. Why has nobody done this? And I really worried about it for a while, and just no, it went back and forth, and no, it's just a really good idea. Do you worry about it? So because I was motivated, because I was motivated by Mars initially, so what drove us? You could ask, what drove us into this weird type of simulation? And what drove us into it is I was trying to measure this really small deformation, this less than 1% change in the length of something. And so I needed a simulation technique that let me measure distances really accurately. And so when you deform a spring by a small amount, you can measure it. In fact, you can measure it to 10 to the minus 16. And that means we can do tidal evolution with this code. We didn't know that at the time. But that's what drove us into it, was this, I was trying to make a body crack and get in the right physical regime for, you know, Charon or Mars to crack. In any case, so because so the original paper, the first paper wrote on this, I needed to tile a surface because I was working with the moon. So I put a shell on it. And so this is needlessly complicated. I'd probably never do this again. But the shell, in order to be stable, needed flexure strength. And we just marked where the springs extended a little bit longer than this limit on the strain. And so the cracks that we simulated were simply rendered, you know, they're like marked. We didn't actually let the material fail. So crack propagation is not easy. And you could put a lot more physics into this. But this shows you what happens when you have a strong tidal encounter in a regime like an icy body like Dione. And you get cracks and rings like this, and they tend to be on one hemisphere. And the reason they tend to be on one hemisphere is because we're in the strong tidal encounter regime. So we're really close. They're really close together. So it's asymmetrical. I mean, normally tidal forces are quadrupolar, but if you're really close, the octopoles and everything else add up. So that's why they're on one side. So we proposed a new geological or geophysical mechanism for moons. and that tidal encounters are a process that happens in space. And we propose it as a possible explanation for these big rifts that are seen in things like in objects like Dione and Charon. And so we know that really strong collisions happen in the solar system, and so we argued that these had to take place, and that the manifestation of them having taken place in the early solar system would be these big cracks. The tricky part is, so we did try and make some predictions for what the cracks would look like, but really we don't have a lot of detail, like how deep, how wide, all those things. So one could do more on that. And we did propose it as a possible explanation for Valles Marineris, but there's a whole lot of detail on the alternative explanations. So you'd have to do a lot of work to compute. So while I was doing this, I ran this simulation. So this is two equal mass bodies. The one that's going around the top is a point mass. And this is the mass spring model. And I'm in the frame of this guy, and you can see the tidal deformation. In the beginning, the thing bounced because it wasn't in equilibrium. But if you go, let's see if I can, yeah, so if I'll go to later in the movie, what you'll notice is this guy is now rotating, and it started not rotating. And so this has been tidally spun up. So I went down to the DPS to present the cracking stuff. And I ran into Michael Fronsky, who works on tidal evolution. And I showed him the simulation. And I said, look, I can do tidal evolution with my code. And he said, well, so his first reaction, so with me, with our code, we have the masses and the dampers in parallel. And that's called the Kelvin-Voigt viscoelastic model. And they like to work with springs and dampers in series, called a Maxwell model. And he's like, you need to redo your spring model to do a Maxwell model. Well, so I'm using the springs to hold it up from self-gravity, so this would have been complicated to do. And so I responded, no, you need to modify your prediction for the viscoelastic behavior and do a Kelvin-Voigt model. And that would have been the end of it, except there was a postdoc there, and he's like, oh, this is trivial. And in like 2 hours, he sent me a prediction for spin down rates. And the next day, I had points online. So let me show you what we did. So what's going on with tidal spin up? So with tidal, if you have a perturber, which I'm showing on the right, and you have a body and it's being tidally pulled, if it's spinning really quickly or it deforms really slowly, this is the slow relaxation, then it doesn't have time to deform, and so it stays around, and then there's no torque. And then on the other side, if it deforms instantaneously, then it's perfectly aligned, and again, there's no torque. So it's really this one in the middle here where you match the time scale of the deformation with the spin, and that gives you the strong torque. And so as a result, there's a prediction for the torque as a function of frequency. So it's tidal frequency in units of the viscoelastic relaxation time scale. And so you get this, you can have it go either way, spin up or spin down, and there's a peak. And so that's what they were predicting. So this is a torque, and it depends on the mass of the perturber, strong function of radius because it's tidal. And then this thing called the quality function that folds in on the frequency dependence. So like you can have a generalization for resistance in electric setting is impedance. Here you can generalize the stress-strain relation in terms of what's called a complex compliance, and it's just a frequency-dependent, possibly complex function. And so your viscoelastic model gives you the quality function. And people usually think of the quality function as a love number times a Q factor, and those numbers come out of our simplifications of more complicated quality function. So this is what they're predicting. And then, so I just measured the torque on my model, and those are the red dots. So that's good. So it has the right shape. the biggest problem that we saw, so the prediction of the Kelvin-Voigt viscoelastic model that they gave me was this purple line, and my red dots are a little bit too high. And so we didn't resolve this. Actually, we published a paper with this discrepancy of 30%. At that time, we were like, well, nobody's ever simulated tidal spin up or spin down with a viscoelastic bodies. So we thought 30% was pretty good error. But it took us a while to track down where it was and what it came from. And we thought, well, maybe it's a numerical issue. But it turns out where the problem was is that most of the predictions for tidal dissipation assume the body's incompressible, but our simulated material is not incompressible. And so the 30% discrepancy comes from ignoring the bulk viscosity in the calculation. So really it was Julien's problem, not mine, but the simulations didn't have the error so far as we know now. So we haven't actually gone back and done better work. So tidal spin down can be simulated directly using a simulated viscoelastic material. This could have been done in the 70s. There's nothing hard about it. You can run it on a laptop. The predicted shape of the viscoelastic response was correct, but with a 30% error that we then later attributed to the neglect of the bulk viscosity in the theoretical prediction. So we got a little bit more sophisticated the following year. And we started doing bigger bodies. And so, and part of this was inspired by Darren Ragazine. He emailed me and said, you got to do Haumea. I was like, well, what's exciting about Haumea? So Haumea is a very elongated body. And so the question is, how long does it take for it to spin down? So we're doing principal axis rotation, so it's not tumbling. And we're wondering about, is the prediction for the torque, when you average over the spin period, how does it depend on body shape? So this is hard to calculate, but easy to simulate because we don't really care if our body's round. So this is what we found. So we were spinning spheres, and the axis of rotation is the axis of symmetry, but they're not tidally locked. And we simulated oblates and prolates. And so all of these dots come from the simulations. Haumea is here. And Haumea has we measured the torque in terms of drift rate for the semi-major axis. And it's about twice as high as it should have been. So it doesn't really explain any of the difficulties they were having accounting for the system. We did find ways to put curves through all these dots using just scaling laws. And so we guessed at how the strain was set by the tidal field, and then averaged it over the orbit to come up with a model that looked like this. So we had a little bit of a discrepancy.
Everything okay at the gallery?
What was that? Oh, somebody's, okay.
Carl Friedberg needs to mute.
Yeah. Okay, so yeah, so that was kind of cool. We actually found the scaling relations that people hadn't predicted analytically. So then we decided to do something more complicated, and that's non-principal axis rotation. So what if you, so if you have a body and its angular momentum axis is not aligned with an axis of symmetry of the body or one of the principal axes, then it tumbles, and so it feels these periodic stress-strain cycles. And those damp, they lose energy, angular momentum is conserved, but energy is lost. So, so the body axes change. Eventually, it winds up spinning around a principal axis, but you can measure the dissipation rate while it's doing the non-principal axis rotation. And there are very good models, analytical models. And so the lines show you the analytical models, and the dots show the simulations. And you can see that over the thing, so these are for different oblates and prolates. So the predictions are for oblates and prolates. And as we vary axis ratio, or we vary the non-principal axis angle. And over orders of magnitude, the simulations are really close to the analytical predictions. So the simulation technique is really precise over orders of magnitude. And that just comes down to the fact that if I take two particles and I move them by 10 to the minus 15 in double precision, I can measure it in the simulations. So really small forces and really small deformations are something you can keep track of while conserving angular momentum with this simulation technique. So to summarize, we can simulate viscoelastic and tidal evolution of homogeneous, inhomogeneous, non-round, elastically anisotropics. I didn't really talk about that. Yeah, Chris?
So, in practice, how many particles do you need to get good convergence?
Convergence, yeah. So since I've been running on my laptop, I haven't really taken convergence tests all that far. And so we did between, a few hundred to a few thousands of particles. And, things are differing by a few percent across that range. What I was more worried about were things like the spring network at the edge of the body, because when you think of a particle on the surface, it's not seeing as many springs connecting to it, so the edges are floppy, and the tidal forces go as really strong functions of radius. And so I was much more worried about that. But so you can ask, why is the tidal torque so good? And the reason for that is almost all the dissipation's in the center. So yeah, so the edges didn't actually turn out to have a really strong effect. So other things that we saw is, what if you do a lattice? We thought about, well, maybe we could speed up the calculation with fewer springs if we do lattices. So we tried hexagonal closed path or something, but then they wind up with certain angles where you get really different so there's anisotropic elasticity. And then, then you're averaging over that. And so those were really bizarre. So those are the kinds of experiments we did. I'm trying to remember which paper. I think it was the Haumea paper. We did those tests. So we did do things with, different densities. We also tracked heat. I was curious. We tracked lopsided tidal heat dissipation in the moon in another paper. But so it really tells you, because it's a simulation technique, you're not as constrained as you are when you're doing analytical calculations. And this field is dominated by analytical calculations. So, and the study of wobble damping shows that the simulation technique is remarkably accurate. And we know how to scale it. So we had to scale, we had to do a bunch of scaling operations to match those analytical predictions. So yeah, so now let's move to a discovery. Can we discover something with the simulation technique? So the New Horizons mission went through the Pluto-Charon system, and there were some surprises, discoveries made when that happened. So to try and orient you, Pluto-Charon is a binary, and then there are 4 satellites. It's basically an exoplanet system with 4 planets, except that it's around a binary, and they're in near resonant chain. It's nearly in a resonant chain. So if you take the orbital periods, the ratio, so the 4 outer moons, you're right, the minor ones, Styx, Nix, Kerberos, and Hydra, the ratio of the period to the Charon-Pluto period is almost 3, 4, and 5. It's not exactly, but it's close. So similar to the exoplanet systems that are near commensurability ratios for the orbital periods. So there were 2 surprises for the dynamical surprises from the New Horizons mission. One is that the minor satellites were not spinning slowly, they were spinning quickly. So people had predicted that they would be spinning slowly. It was known they were regular from Hubble Space Telescope light curve observations. And so they assumed they would be like Hyperion in chaotic tumbling states. But when they got there, they found out they were spinning really fast and not well, they didn't know they were not tumbling. They're definitely not tumbling. It's much harder to have something tumbling when it's spinning quickly. So this tumbling was predicted but not seen. And then the other surprise was that all 4 satellites had high obliquity. And so that means the spin axis is tilted with respect to the orbital plane. And so showing you this is how they presented the data. So the orbital direction for Pluto-Charon orbit is here in this direction on the sky. So this is pole deck versus pole RA. And these are the directions of the spin axes for the 4 satellites, and they're nearly 90 degrees apart. So they're like tilted down like Uranus is. So that was a surprise. So in hindsight, if you estimated using guesses for the material properties, they shouldn't have spun down actually tidally. So oddly, there were 2 papers that predicted this tumbling based on the assumption that most satellites in the solar system have spun down and tidally locked, or nearly, or not locked if they were not round like Hyperion. So how is the system formed? And so how do we explain, or do we want to explain these obliquities? So if Styx, Nix, Kerberos, and Hydra, we could ask, are those obliquities primordial? So they were probably born in a disk because they're all in the same plane, low inclination, and they have these nearly resonant chain orbits. They're low eccentricity. So that tells you, yeah, probably born in a disk. So if accretion if the satellites form from accretion of small stuff like gas or pebbles, then it would retain the angular momentum of the disk, and then the obliquities should be 0, so you should have the same direction as the disk. But if there was a late stage of accretion, then you might have collisions, and it might realign the spin directions. So the fact that they're clustered around 90 degrees, is that odd or not? So independent of that, I was just like, yeah, let's see if we can find a mechanism that would tilt them over. And you don't know if it's right or not necessarily. So we had been doing stuff like this, where we were simulating for a few dozen orbits with lots of particles. Now we need to simulate a lot of orbits, like thousands, 100,000 orbits. So we went to poorly resolved bodies. So the simulations are going to look like that. So this kind of shows you, the scale. Space is big. So that's Pluto-Charon, and now you're zooming in. This is actually a snapshot of an actual simulation. That's the thing that we're simulating. It's a non-round body, and it's orbiting a binary. So what do we see? So we first started doing tidal spin down. So we let it use the fact that the code can damp to let it slowly spin down tidally. And so you're seeing the spin rate drop here. And the obliquity for Styx simulations had intermittent behavior. But as the thing is spinning down, so this maybe we're catching it now in a state where it's in a high obliquity state. One of the things you see is none of this resonance. So these are resonances being crossed. None of this is really accounting for that. So what causes that? We have to figure out what's the dynamical mechanism causing that. When we did simulations like this for any of the other satellites, like Hydra, they were really boring. Like basically nothing happens. So tidal spin down alone, the mean motion, the spin orbit resonances, so that's when the spin period matches some multiple of the orbital period, we're just not causing excitations. We did see interesting phenomena. So you can see like there's a spin binary resonance in one of these. This was a Kerberos simulation. We saw tumbling excitation, trying to figure out what causes tumbling excitation, which frequencies are being matched. So the simulations are not, they just see whatever's there. And then it's up to you to try and figure out what's causing it. So you may not, your theoretical setting may not be good enough to guess at all the possible resonances that are important. So we're using the simulations to do that. This is a blindly sweep through parameter space to find what interesting resonant behavior might be around. So this is what we found. And so in this case, instead of using tidal spin down, we're drifting and slowly expanding the Pluto-Charon system. And what that does is it moves the orbital resonance, this 3-to-1 orbital resonance, and past the system. And this is a Styx simulation, but as this resonance, so this is captured into the 3-to-1 resonance, you can see this is the orbit divided by the binary orbit period, so that's Pluto Charon. At the same time, the orbit tilts, so it's a resonance that involves the longitude of the ascending node. But at the same time, that top plot shows that the obliquity just really flips. And so this is a resonant mechanism that involves a mean motion resonance and changes obliquity. Yeah, so we saw the same thing happen in the hydro simulations. So if we can figure out what causes this, we can probably account for the intermittent variations in the 6 simulations without drifting, drifting Pluto Charon. And this type of thing probably could have worked on all of them, all of the 4 minor satellites, because they're all near mean motion resonances. So if it's a mechanism that works near mean motion resonances, it really would operate on all of them, accounting for all of their high obliquities. So what's the orbital resonance? So whenever you have 2 periods that are close, they're an integer, one of them's an integer times another one, then you can write that relationship between the periods. You can invert it. You get a relationship between the frequencies. So this is angular, these are rotational, angular rotation rates. You integrate that, you get a condition on an angle. Resonant angle. And so those are things that you might be able to derive using a theory, meaning you take some Hamiltonian and expand it, and you're hoping you get a term that has that angle in it. And then the size of the amplitude of that term would tell you how strong the resonance is. So the first thing to try and figure out what resonances are likely is to go look for frozen angles. And so that's another technique. That's a technique for finding what resonance would be important in a system. So, so for angles, we have to include angles that are relevant to the spin. And so an angle that is related to spin is the precession angle of a body. So you take the spin axis and you project it down onto the orbital plane, and you keep track of that angle. So we measured that numerically, computed numerically in the simulation, and then plotted angles and see which angles are frozen when the obliquity increase happens. And so this angle winds up being frozen when the obliquity is changing. And this is an angle that involves the location of the satellite, the angle of Charon, so that's the binary angle, and this is the precession angle. So we can call these mean motion spin precession resonances, maybe. So, and then, yeah, so this, how do we think about, well, physically, what is this? So what it is when it's going around in the orbit, you're matching the precession time scale with the orbital time scale. So if you have a precession, so anything that's spinning, if you're perturbing it on the precession frequency, you can cause it to tilt. And so that comes down to the top, right? And so gyroscope is something that's spinning, and it will precess. And if I perturb it at the precession frequency, I can get it to tilt. And so we'll see. So if I start doing, I have to get it to tilt over a little bit there. Now it's tilted over, but now if I start perturbing it at that frequency, it really either tilts up or it tilts down. So if you get good at this, you can get it to stand up or stand up. But that's basically it. Perturb it at the matching with the precession frequency. It'll tilt over. So to summarize, the tidal spin down times are long for Pluto satellites, and they haven't spun down. And in hindsight, that's not surprising, actually. Tidal evolution alone doesn't really explain the obliquities. It can kind of explain sixes, but we don't know why. With the spin mean motion resonance, you can explain those intermittent obliquity changes. Outward migration of Charon causes capture into a resonance that really rapidly changes the obliquity of the minor satellites. And it's a commensurability between the spin precession rate and the mean motion resonant angle. So, or mean motion, should have said mean motion there. So you can develop a theory for it. There are 2 approaches for that. So Sarah Mulholland has theory that depends on matching precession rates, where the precession rate gets strongly changed near mean motion resonance, or you can work with a direct torque. Maybe both are important. So we wrote a paper expanding Hamiltonian out with direct torque and showing you that the strength of these resonances are not even low in, I mean, they're not low, they're not high order in inclination or eccentricity, which means they're strong. And they would work for all of the satellites. So perhaps all these satellites were previously in mean motion resonances, and that's when the obliquity changes happened. Okay, so moving on. So after this, so this is work we did this summer, actually. So we were curious about binary asteroid evolution. So it turns out that a third of near Earth objects are binary. And binaries are going to be in the news a lot because, because in September, there's going to be an impact with a binary. So the DART mission is on its way, and it's going to slam into this thing at like 6 kilometers a second, and it weighs 500 kilograms. So that's like a big impact. This thing is dimorphous. It's the secondary for the primary. These are, people don't really know what they look like yet, but, and I doubt it looks like that. But this thing is only like 160 meters big, so it's going to really do damage. So, so there are two big mysteries in binary asteroid evolution, and I'm going to propose a single way to solve them both, so that's cool. So tidal dissipation estimated from tumbling damping in single asteroids gives a really different number than estimates for binary asteroids, and it's orders of magnitude different. So there's a discrepancy in estimating material properties. The second mystery is radiation effects cause the two asteroids to drift in semi-major axis, and that's called biorp. So Yorp effect is spin up or spin down. Biorp is the torque on the, by radiation on the secondary causes the orbits to either diverge or converge. But the surprising thing is how fast it's predicted to happen. It's predicted to happen in less than 1 million years, and then they would fall apart. and yet, near Earth asteroids, their lifetime is like 10 million years. So there's an issue accounting for their lifetimes. So one thing is this biorp always assumes they're tidally locked. And so that's a thing we could question, actually. So moving on. Oh yeah, here's a simulation. So now we're actually going a little bit more than past what we've done before. We were only doing point masses with one resolved body. We've got 2 resolved bodies. And this is, we're in the frame so that these are same axis. And this one, you can kind of see it, this end is always pointing towards that guy, but it's rocking back and forth. And so this is in a non-principal axis rotation state, even though it's tidally locked. So that's going to be kind of the take-home message, actually. So yeah, so the 2 resolved bodies means the gravitational field is very not round, and that is expected when you look at the asteroids. They're not round. So we're used to doing simulations around planets that are much rounder. Binary asteroids are significantly non-spherical, both bodies. So this is a simulation of tidal spin down. So you can measure the rate, tidal spin down rate, which you can see at the top in this really short times blue thing going down like that. But the second panel shows you the obliquity. And so at this point, it enters the spin orbit resonance. So that means that long part is always aligned. So it's in a spin synchronous state, but its obliquity and this, which is the non-principal axis angle, are remaining high for a really long time after it enters the spin synchronous state. And so that's what we were seeing with it. It's aligned, but it's rocking back and forth. So, so this is a long thing. So why does it take so long? Because we'd run simulations of Deimos and Phobos and not seen it take so long. We attribute that to these multipolar coefficients that are present in the binary asteroid setting because they're really not round. So yeah, so Secondary is often assumed to be synchronous. And so that means the biorb, and synchronous with no rocking back and forth. And so that means the biorb calculations assume that, and that's why they're getting these really fast drift rates. But there have been lots of proposals to get around this problem of how do we keep asteroids, binary asteroids alive. So I gave some suggestions. Maybe they're born at smaller radii, maybe they're really soft, and so they have, and so this is part of the discrepancy. They have different material properties than regular asteroids. But basically, light curves that find that most many binary asteroids are unspin synchronous states are not going to be good enough to see if they're rocking. And so, so this is what I'm guessing is the solution to the problem, is that better light curves, or you actually get to a binary asteroid and look and see what it's doing. So, so what are the motions? So if you think of an airplane, there are various motions. Direction to the primary is when the long thing is the line like this. And this tilting back and forth, you can also call it roll. And I called it short axis tilt before I was aware of Batia Tuk's work where he talked about barrel roll instability. So this instability has also been seen in other people's simulations, not with the tidal spin down setting, but so yeah, I already showed you this, but it's the same point. So let's move on. So, so what if it tidally locks? What happens afterwards? So if biorb starts up and then the system is drifting, do we see other resonances that can excite the spin? And we do kind of in some settings. So we do see some obliquity jumps if you have an inwardly migrating system where the two are approaching each other. We didn't see any interesting phenomena when things were drifting apart. So even if the system damps down and winds up drifting quickly, it could maybe kick itself out of a principal axis rotation state and wind up back in a more interesting spin state. So let's get to the question of, does the biorb torque change? So I mentioned that all biorb torque calculations had assumed tidal lock with no rocking. And so we decided we would try and take our spin dynamics simulation output. We can record the angles and the orientation of the body in the simulations. We wanted to tie that to predictions for the torque from the radiative forces. So that comes down to taking a shape model where you have facets and you add up the radiation forces from each facet. And so so I'd never done a radiative torque calculation before, and so figured the chance that I got it right the first time was 0. So so we went and found a shape model where somebody else had made a prediction from that shape model. So we're using the Squanit shape model because there was a prediction, somebody else had predicted. We wanted to make sure our code was giving the same answer. So so that's the original one, and then we did things like make it rougher, and we made it a little bit coarser so that we could speed up the calculation. So just taking the Squanit model and tilting it back and forth arbitrarily with different angles, we found that the torque from the biorb was strongly dependent upon the extent of the tilt. So this is not from a simulation, but it does tell you that it depends on the angle. So the next step is then to take all the instantaneous angles for the spinning object in the simulation and then compute the biorb torque. So the other thing is that red dots match the black circle. So this is really important because once we got the red dot near the black circle, we knew our calculation was consistent with those in the literature. So we're not measuring garbage anymore being the key thing here, because we started off. So how did we figure out how to get the body orientations out of the simulation? So we have a bunch of particles. So this is kind of cool, actually. So you use a covariance matrix that depends on the differences in the particle positions at one time and another time in the simulation. And that gives you can turn that into a quaternion that then you can use to rotate the body. So using this trick, we can get at every output of the simulation and a rotation that would rotate the body back to what it had been initially. So we actually know the rotation, and we can take a shape model now and rotate it, compute the Biorb torque from it at every moment in the simulation. So we're not evolving the simulation with the Biorb torque, but we are computing what the torque would be at every moment in the simulation. And this is what you get. And so during the time when you have a lot of non-principal axis rotation, the Biorb torque, which is given in terms of this dimensionless number called the B coefficient, averages to 0. And then the system drops down and the non-principal axis angle is smaller. And during the later times of the simulation, the Biorb coefficient, the B coefficient, slowly rises until it eventually approaches the value that would have been predicted for a tidally locked, non-rocking situation. So it really does show you that this rocking just shuts down the Biorb effect. So to summarize, non-principal axis rotation in an asteroid secondary is long-lived and should actually, last a significant fraction of the lifetime. And it hasn't been detected. So, so we're predicting that asteroid binaries, the secondaries, are in non-principal axis rotation states, and that's going to account for their lifetime. And so maybe we'll know when the DART mission gets to Dimorphos and before it smashes it. Maybe they'll be able to measure the rotation state. So you can also measure rotation states with radar. So and light curves. So it's something that we want people could either confirm or refute, right? So because the non-principal axis rotation shuts down the Biorb torque, it's a way to extend the lifetimes and make them make more sense without having odd material properties predicted for binary asteroids. So, and I see that my timing is not terrible, actually. Yeah.
So we'll take questions from the room and raise your hand on Zoom. Okay. Catherine, Chris, Drummond, and then we'll go to Zoom.
Yeah, I guess following up, someone stole my question earlier about particle number, but it's really about setup and how do you relate the setup to the real universe? Like, how do you know about the spring constants and the lengths of within what media you connect? Within what media do you connect the springs to particles? Or vice versa, do you set that and then learn something about it?
So it sounds like the question is, how do we choose numbers of particles and springs? Yeah, so I have a really low attention span. And so I always do the fastest thing, which is the least number of particles I think I can get away with first. And then I double it to finish the paper. No, so I'm sorry. No, so it depends on the problem you want. So for these heavily, like with lots of particles, we're only measuring things for fractions of rotation states. We try to run it with enough particles so that it's not being affected by the numbers of particles. But the random spring model, this random mass spring model, you don't want particles too close together because then they're not really part of the thing. So when I choose the particles, so I choose random numbers and then I either accept a particle or not. I don't let them get ever too close to each other so that there's a range of particle distances between each other. And then you just keep generating particles until you stop being able to fit them in. And so that gives you a range of distances between the particles. Then the springs, we connect up all pairs of springs up to a certain length. And you need to have a certain number of springs per particle. Otherwise, it acts like a really patchy foam. And when you stretch our foam, it's like you get these really big holes in it. So you don't want that in this because you want it to act like a solid. So the number for that is like 15 springs per node. And that number comes out of Cott's tests where he did a static beam test. And he was like, when does my prediction for the Young's modulus match the analytically predicted dip for a static beam to deform under gravity? And it started matching with 15 springs per node. And so we adopted that as the minimum So you can play around with more complicated spring networks. And supposing you wanted to do something auxetic, like you pull it and expand it or something, you can play games with, I'm only going to make stiff springs that are small and loose springs that are big and get foam-like behavior, all sorts. And so there's a whole field of like, let's do interesting mass spring networks to get interesting material behaviors in terms of young modulus. And so, or in biophysics, you see people doing like cartilage modeling where they have very nonlinear properties of these elastic materials. So you could do stuff like that if you wanted to. And I did play around with this a little bit because I was kind of hoping to get an incompressible solid model because ours is compressible. But I never really succeeded in something that was nice. So it's something we could get back to. I'm not sure if this answered your question, but but just to kind of give you the feeling for the complexity of what kinds of things you could think about doing. So for the long simulations, we just under-resolve the body and don't worry about resolving the features in it. And I think the largest particle simulations we did were ones we were trying to map the internal heat distribution. So we tried that with the moon.
Hello.
Yeah.
Well, great talk. I had a question about at the beginning you had like those great simulations of was like drive-by like tidal encounters.
Yeah.
And even in the first one you showed, it seemed like after the body had already passed, the planet was still like fluctuating in a way like ringing like from that last encounter. So I was curious if you had any idea of how much heat that could generate internally within these planets, and what could the consequences of that be for, say, like an ice world like Sharon, which is out in the depths of the solar system, since like an icy world, what that heating could do.
Yeah, so I think in all the settings that we simulated, the heat budget was irrelevant except for the moon. And so mapping the internal heat distribution for the moon was the one setting where we were really trying to understand where the heat went inside. But that doesn't mean you couldn't find a setting where you would be more interested in the heat. So the ringing, it is showing normal modes. And if you take that and you decompose it and take a Fourier spectrum of it, you'll get the normal modes. So we did that in one paper. It was like, actually, we were following this paper called apple seismology, where somebody was measuring the normal modes of an apple, and because we had uniform density model, we were like, we don't want the Earth because the Earth is not uniform density. So the apple seismology paper was awesome, but we matched the spectrum really well. And then the damping rate. So oddly, with these tidal things, damping is always at the bottom. And that's because the tidal stress is largest at the bottom. It's very counterintuitive because you think of pulling, it's deforming more on the surface, but the heat is always at the bottom of whatever shell that you're working with.
Mine is a very quick point, and I'm not old enough. Oh, yeah, quick point. I'm not really old enough to do what I'm about to do, but I am more of a comment than a question. So apologies, but it's something I've thought about is the Yarkovsky effect on asteroids. And I was trying to find a paper. I can show you this later, but the surface you showed was really cool. You showed that when you went to coarse, things changed, and there's been cool work showing that actually if you take into account the cratered surface of an asteroid, it can actually significantly change the torque on it. So it's something you might look at.
Oh yeah, so with this thing, everything would scale with it, and so it doesn't actually invalidate whatever I was trying to show. But trying to understand the Yarkovsky effect and how it's affected by thermal effects as well as surface roughness, and whether there are valleys, and this is like a huge set of literature, and I don't think it's resolved. It's not resolved at all, right? So and also I found so there's this nice paper by an Israeli group. I forget who the first author was, where they tried to come up with a roughness statistic and then match that to the Yarkovsky and the Yorp and the BioYorp. And so they may be the only one that had kind of a qualitative like feeling where you understood how it scaled. because I find when I was picking a body, I'd look at the body and I'd go, can I predict whether it's big or little? I had no idea. But I think we were doing the most vanilla, simplest model with no thermal, no conduction, nothing, no hot valleys and cool surface, so nothing that is part of what people worry about with thermal models for Yarkovsky effect.
And I'm not seeing any questions on Zoom, and then just one last question.
My question was very similar to Catherine's actually. I was wondering about the relationship between the equational state and the strings that you pick. Like if I wanted to do these for a binary star, study the tidal evolution of a star, maybe I'm too naive, and you would expect a relationship between the strings that you choose and the equational state.
Yeah, so this particular random mass spring model, the Poisson ratio is quarter. And so how much deformation, I think it's fairly linear in terms of pressure, what the density, how's the density vary with pressure. So it's much simpler than anything anybody would use for a hydrodynamic setting. So I was discussing it with Chris, and you should discuss this with Chris. Like, what would you have to do interesting tidal angular momentum conserving tidal models for stars, which are hydrodynamic? So we started with SPH with this, and I couldn't measure the deformations well enough. And SPH I think has a problem with angular momentum conservation. So I mean, would that not work? Or not? So I don't know. I mean, it's an interesting question for future work. Right? So what could be done? But in any case, Chris was also interested. So
Sprints will have difficulty with differential rotation.
Oh yeah, I mean they would be terrible because yeah. I mean I've basically been doing solids, not anything that flows or is plastic or ductile, right? So yeah, I mean this doesn't mean that solids are boring, but. I'm not sure if it would help you with binary stars.
Okay, great. So we have a reception outside, also a welcome for our current crop of pre-doc students. So we'll see you.
So I was going to introduce them, I'll actually.
Oh, you did this here, great.
Oh yeah, I thought that was supposed to be first. Here, let me get out of the way here.
So hi, everyone. As most of you or many of you know, I'm sure, we have a new class of pre-docs that arrived at the beginning of February. These are students from around the world, different institutes that spend 5 months working with one or more CCA mentors. We wanted to introduce them and welcome them. That was delayed a little bit because of Omicron, but now that we can have receptions again, we decided it's a good time to do it. So I'm just going to very briefly introduce everyone, and those who are here can stand up or at least wave. And apologies if I mispronounce your surname. So first, we have Alex Gagliano, who's from Illinois. He's over there. So Alex is here working with Gabby Contardo, Dan Foreman-Mackey, David Hogg, and Shirley Ho. His project is called Reinforcement Learning Recommendation Engine for Targeted Transient Follow-up. And then just for introducing, and so you can kind of hook into something for your memory, I've stolen one of the interesting aspects about them from their slides. So for Alex, I note that he raced a double metric century on a 3-person bike, which sounds awesome. And personally, I'd like to learn more because I've only done a imperial century on a 1-person bike. So this sounds even more interesting. Next, we have Mike Lau from Monash. Hi, Mike. Mike is working with Matteo Cantiello and Adam German on hydrosimulations of planetary engulfment. And Mike has a sword carrying license in Australia. I don't know whether that translates to New York City. So, beware. Next up, we have Sophia Lillingen. Did I slaughter them? Lilla Engen. Okay, thank you. Coming to us from Surrey. She's working with Adrian Price-Whelan and Catherine Johnston on information content in stellar streams and time-dependent potentials. She has once jumped out of a plane and took a selfie with quokkas afterwards. I had to look up what those are. They're apparently short-tailed scrub wallabies.
They're the cutest things ever.
Yeah, they look very cute. And my Google search revealed that fact about them. So very cool. Next, we have Manami Roy. Hi, Manami. She's coming to us from the Raman Research Institute. She's working with Kung-Yi Su, Stephanie Tonneson, Drummond Fielding, and myself on the effect of satellite galaxies on the circumgalactic medium of the host galaxy. And in her spare time, she likes to play the ukulele and sing. So welcome. Then finally, we have Brent Tan. Hi, Brent. Brent comes to us from UC Santa Barbara. He's working with Drummond Fielding, Greg Bryan, and Yanfei Jiang on the fate of cold gas in galactic winds. And Brent is a big fan of Brandon Sanderson's books. All right, so welcome to all of our pre-docs. If you see them around, please say hello, have a coffee, have lunch, whatever. And I hope that all of you have been having a good time so far. As I've said before, if you are, or especially if you aren't, please come talk to me. And yeah, we're very happy to have you here. So please go enjoy your food and drink. Thank you.